Hi everyone, Joe here, and this is lecture 2.1 for module 1 in RAD104. And in this lecture, what we're going to be talking about is radiation safety in a fluoroscopy environment, just because that's where we're going to get most of our dose as occupational workers. So it might be a good idea to understand how to keep ourselves safe and some of the safety features that we have in the room. And so let's get started. All right, so it is true that you're going to be getting your highest amount of occupational exposure by doing fluoroscopy. However, I should note that you're also going to be receiving, or you could receive, a high amount of dose by doing portables. And so some of the things that we talk about in this lecture can also be applied to when you're doing a mobile or a portable exam. Now, in both fluoro and in mobile radiography, you're never going to be standing in the primary beam. So where do we get our dose? And I've mentioned this before, that it's the Compton scatter that we deal with. And scatter is considered a secondary form of radiation. So we're not really going to get our dose by being in the primary beam. From time to time, you're going to be very, very close to that primary beam. Perhaps you've done a fluoroscopy exam where you had to hold a cup for somebody who might be drinking from a straw while they're lying on their side, and it's difficult for them to hold. So yeah, is your hand going to be close to the primary beam? Possibly. So you could get a little bit of exposure from that. But for the most part, it's really the scatter that comes from the patient itself that gives us our dose. And this is the same for any mobile radiography too. Since we're talking about dose, we really need to understand dose a little bit better. And it's never that simple of, well, how much radiation did I receive? There are different kinds of radiation doses out there. Some of them are going to apply to all types of radiation, and you're going to find out that some of them also take into consideration what part of the body has been irradiated. So let's dive into those different kinds of radiation doses so you get a better understanding of how it's measured. So the word exposure, if we look at the word exposure and we don't really think too much about it, and we just think of our past history with the word exposure, it basically is, have you been in the vicinity of something? So with radiation, we're dealing with, were we exposed, or are we in the vicinity of radioactivity or radiation? You've probably heard with the whole COVID thing, have you had any exposure to anyone with COVID? So were you in the vicinity, or were you in the area of somebody with coronavirus? So that's how that word is going to be used. But of course, what we're going to be dealing with is more radiation. So exposure expresses the concentration of radiation delivered to a specific area, such as a surface of the body. Did we walk into a room with active radiation, with radiation? Were we exposed to that form of energy that could affect our body? Now, exposure to radiation can be measured in one of two ways. You're either going to see it as coulombs per kilogram. All right, a coulomb is a measurement of energy. So a coulomb is a small amount of energy per kilogram. So per kilogram of tissue, per kilogram of whatever material you want to call it. So that's one way to measure exposure, coulomb per kilogram. Or for our purposes, we usually call exposure in the form of a Roentgen. So Roentgen, when dealing with x-rays, if there's so many Roentgens in the room, that'll tell us the amount of radiation or the amount of exposure that's happening in that area or that room. So with exposure, we deal with air kerma. Air kerma is and you probably, if you're reading this top bullet, you might be wondering what SI is. System International. So the international system for exposure in the air is air kerma. So if we've got radiation in the air, so radiation coming from that's in between the tube, the x-ray tube, and the image plate, right in that area, when we hit the exposure button, there will be air kerma. There will be a certain amount of radiation in that air. And so that's how we would measure that. Whenever we're dealing with air kerma, we're going to say that it is measured in gray. A lot of times when we're dealing with x-ray, we're dealing with a small amount of grays, so we call them milligrays. So air kerma is just the amount of exposure in the air in a particular area. And we measure it in gray. So when we're talking about air kerma, we can talk about air kerma in a couple of different ways. One is, how much radiation is in the air. And that's not a big deal, okay? We can measure how much radiation is in the air. But that doesn't have anything to do with exposure. What about us? You know, what if I was in that air? What if I was in that beam? And so we're going to be looking at air kerma with regards to my tissue. So if I've measured the amount of radiation between the X-ray tube and the image plate, and I can measure that radiation going through, what happens if I put my hand, all right, or any part of my body into that X-ray beam? Okay, that measurement would be written a little bit differently. When air kerma is used to describe the kinetic radiation in the air, it's written as GYA. However, we put a body part in there, and then it's going to be called GYT. So when air kerma is used to describe the kinetic energy absorbed by tissue, it's written as GYT. So air and tissue. So that's what the little A means, that's what the little T means, and that is air kerma. And that is talking about exposure to radiation. Now, I think I've talked about dose area product before, but what dose area product before looks at is the square area of what's being irradiated. Okay, so when we take an X-ray, if we take an abdomen, I'm trying to think if we cone down on anything. Well, let's just take the abdomen. So if we take the abdomen, we know there's so much dose that's coming out. We've set a kVp, we've set a mass, okay, and we have our light field as a 14 by 17. All right. It takes into the consideration the size of the light field, the size of the amount of radiation coming out. Okay, so not only do we know the exposure coming out of the tube, but we look to see how big the light field is, and that's going to give it a higher dose area product. If we decide to do a bladder shot, let's pretend we clipped the bladder on our abdomen. We keep the same technique, but now we cone right down to maybe a 10 by 12 plate, and we just want to see a picture of the bottom half of the bladder so that we see the pubic symphysis. The dose area product is going to go down, because even though we're using the same amount of radiation, we've just made the amount of radiation coming out smaller by coning in. So dose area product really is still the exposure, but it's taking into consideration how small or how big the light field is, and that's what dose area product is. All right, so this leads us to absorbed dose. So we have exposure in the air, and we've put a body part in the way. And so that tissue has absorbed some radiation. It has absorbed some energy from that radiation. And so we're going to call that absorbed dose. Whenever there's some type of absorbed dose, we know that there's going to be some type of biological damage as a result of that radiation. Now, the amount of absorbed dose has a lot to do with what is in the way. What type of tissue is in the way? How dense was the tissue? What's the atomic structure of the tissue? So all of those things, the atomic number, the mass density, all of that will affect the amount of absorbed dose by that radiation. On top of that, don't forget another reason why we have high absorption is that we didn't give the radiation enough energy behind it. We didn't have enough kVp for it to penetrate and go right through that patient or through that tissue. And so if it doesn't have enough energy to go through, then it's going to cause more absorption. And the more absorption you have, the more biological damage you'll end up having. So basically, the thing to remember is that absorption will increase when the atomic number and mass density is high or is increased, and the photon energy or kVp is decreased. An absorbed dose, just like air kerma, is also measured in gray or GY. And guys, just to be mindful of time, I'm pushing 9 minutes, and what I want to do is stop here because we're going to go into another couple of types of doses, and they are going to take a little bit of time to explain, so I don't want to go too long with this video. So I'm going to stop here, but in our next video we're going to be talking about equivalent dose and effective dose, which are a little bit different than absorbed dose. And so you need to know that information, and I look forward to talking to you all about it. So any questions about what I've mentioned here, please let me know. Otherwise, I'll see you at the next video.